Welcome, Johan, that we present us Erly Marsh model-based testing tool. Thank you.
Thank you. My name is Johan Blom. I recently got my PhD after, well, I actually just spent a little bit more than 10 years on this particular thing, but I have actually spent more time on my PhD. Anyway, this is going to be a talk about a tool that I used as part of my thesis. And it's going to be, I'm going to do it quite a bit of overview and more like an introduction to the tool. So why do I start doing this, developing a model-based tool? Well, one main reason was that I was working at Mobile Art at the time. And we were developing large server software, location servers, SMSC, etc., for the telecom operators. And all of those systems were situated at the operator's domain, meaning that they have to work, and they are really big and complicated. Some of our systems hundreds of millions of users. Mobile Arts were founded by a set of very experienced developers, but we were no testers. So we were focused on developing, we were a startup, we were focused on developing our stuff as fast as possible. We didn't really have time to think of testing, etc. So we were thinking a little bit about this, how to test. And I identified a set of core modules in the location server. We had already developed it at that point in time. And we had also deployed it at our first customer. So it was kind of working. I was running a dialyzer on it, and it looked okay. And we also had some manual test suites, also going fairly well. So, I mean, basically, everyone was kind of happy. Everything was working okay. That's what's like the common belief. We had this accepted customer, etc. I wasn't so convinced, though, that everything was as good as like was the common thought. And the reason was that, I mean, these manual test suites were only testing a small part of the system. The systems, again, they were quite complicated, and there were a lot of use cases in it. And again, these products have to work all the time. And perhaps particularly important, they don't have to interfere with the network entities. We are inside the telecom operator's domain. We have access to all the sensitive nodes in the telecom domain network, like the HLR, for example. We could potentially completely crash a network. Then I had some ideas about model-based testing. I knew what it was. I had started my PhD studies before, so I knew it from university. And model-based testing is about, it captures functional requirements. It talked about formal executable models. And we generate test suites from these models. As they are formal, I can generate these test suites from the model. As we can do this automatically, we can use tools to generate the test suites from the models. And indeed, there exists a set of set of tools for generating test suites from formal models. Qtronic, Spec Explorer are examples. There are many more. They are quite expensive, though. They are not specifically targeted to Erlang, to the Erlang world. They're more like common. So what I did was I started to develop my own tool. Of course, it's always best that way. So this is just what the rest of my talk is gonna be about as a kind of a map. In model-based testing, you need a model that captures the requirements of what you want to test. And in doing that, you can do this in many ways. You can create the complete model and then you test it. That was how I did it. But you can of course also create this model step by step as your product grows in a more agile way. And you need a modeling language to express your requirements. And I'm dealing here with abstract models again, capturing functional protocols, specifying protocols, a little bit more advanced systems. So Erlang is perfect for that, I thought. We have all the necessary things we need. And of course, it should be really easy for Erlang developers if they already know the syntax in the specification language as well. And another advantage is, of course, that it allows reuse of the existing Erlang infrastructure. So what I did here was to introduce Erlang as a specification language, but I don't need the full power of Erlang for my purposes here. I don't need traps, for example, or I may need process messages, etc. But I'd choose to not cover that here. So basically, it's just the basic functionality of Erlang I'm using, which is okay here, I think, because it's just an abstract view of the systems. So here is a typical state machine, and you start in the green blob and end in the red blob. There are several paths through this, and one of the paths is this. Just as an example, you have you start in the idle location. You get an input event SLEER with 6 arguments, and you output some output events, 2 of them in this case. And then there are some guard on this edge, and there are some actions, you update state variables, etc. And we can express this in Erlang quite naturally. We are in the idle state. We have this SLEER event. We have these arguments. We have this guard when in forth, PSI equals false. Then we have something a little bit different there from ordinary Erlang. We have a function. You cannot use that because it's a side effect. This is okay here. I allow it here because in this case it's a configuration function. It's a static data, and it's something well defined in this language here. And we can see that if this first is record is true, then we call this function send FSM. It's defined here. It's very simple. And FSM is not further defined, which means here that is an output event that needs to be defined elsewhere, but not within this Erlang FSM specification. Okay. In this case, I can evaluate this in 2 different ways. Given that either this record is true, given that this of course is true, this guard here, and I get this match in the first line here. I can either I can do so I end up in this next state force update, meaning that I go to a new location force update, or I end up in this access next state access net param. So there are 2 ways of executing this. And that's how I deal with it. I execute symbolically all the possible ways that I can. So it's kind of a partial evaluation symbolically of the Erlang code. And that's what I work with later on. Okay, we got a lot of these edges. and we got a lot of possible test cases. One of the problems you face then is that you want to select a few of them, and this is not actually the observer that you may be used to in part of the OTP. I actually invented this before the observer, but I was too slow to release this. This observer here is used for specifying which test that I want to be part of my test suite. Because typically you can execute your model in so many ways, and you get so many test cases. You have to select some of these test cases. Also, there are other practical limits on a test suite. I'm talking about larger systems here which operate in a more advanced, complicated environments. You may have latencies, you may have timeouts when actually testing these systems. So the problem is how to generate the best test suite with a bounded size. Well, a solution here is to use these observers. And the idea is that this should be kind of general. A coverage criteria is supposed to fulfill some requirements you have on your system, on your test, what you want to test. And from the literature, typical examples are that you cover all locations of your model, or you cover all edges or definition use pairs, for example. You define a variable and then you use it. But it's unclear when and what coverage criteria to use. And that also calls for some flexibility, because you don't really know what to use. And you may also want to test to invent your own criteria. Yeah, the motivation is quite simple, obvious. You may want to specify any coverage criteria, and you want to make it possible. And those commercial tools that I mentioned in the beginning, they do not really do that. And then we do this and implement this by implementing this observer, and that's a kind of another state machine that observes the execution of the EFSM model. So this is what a typical observer may look like. Observers are in general much simpler, and this is a kind of complicated observer. It's a definition use, where you define a variable on the first edge. There's actually these are supposed to be arrows here. You looking for a definition of a variable, and on some particular edge. And you can see here you're looking for a defined variable on some particular edge. This looks kind of Erlang, but it's not quite, because you have X and E here. They doesn't occur here. So it's a little bit different here. X and E are rather bound in a more prologue fashion by something we call match variables. It's hidden here, but in the definition of the is-defined var and is-edge, you have these definitions, and you can define your own observer predicates. And then, of course, there could be more than one variable defined on one particular edge, meaning that actually this is not just one observer automata that is executing. It could be many. It could be hundreds, thousands operating concurrently when running the execution of the Erlang FSM model. So how does it work? Well, we have this run. This is like an ordinary run. We're executing the model, so it's like we are executing an Erlang program, really. But then we're also monitoring the syntax. And we need that in order to see which variable that is defined, for example, or on which edge we are currently. So here in the observer, we observe that we have a definition of MSID, and we are on E1. Okay, that means that we can proceed to the second observer state. The execution of the Erlang FSM model continues. We are on the fourth update, and we move to the updated state. Okay, there's no definition of MSID in that state, so we stay in this DU1 observer state. And okay, I'm stuck. I got stuck. The idea was that it should continue there. Well, I don't know what's happened. Sorry? Sorry about that. I don't know how to get out of this. Pardon? No, this is just. I seem to have got stuck in somewhere here. I don't know what happened. I must have typed something. I must have done something stupid somewhere. Well, I don't know how to. I was running short of time already before. Okay. How many minutes do I have now? Okay, we ended up in that state, and we have we have reached a matching observer state, and we have also reached a final state in the EFSM model, meaning that this is an accepted state. Okay, I have to speed up this even more. Okay, we have a problem here because we are dealing with symbolic test suits. And the reason we are using symbolic test suite is because we got a complexity problems here. So symbolic execution is a way to handle sets of executions. And we have adapted this to this model here. There's a lot of theoretical stuff, so I have to skip this, of course. But we end up with a test case that contains symbolic parameters. And we get a set of symbolic test cases with symbolic parameters that can be instantiated in many ways, possibly. We have to select one or more of these possible instantiations to get abstract test cases. From abstract test cases, we can generate concrete test cases. And the concrete test cases are those that we use then that we execute against the system that we want to test. Okay, so that's basically it.
Thank you.
Yeah.
We may have time for one question, but not much. Any question?
So basically, you said that you can kind of have a special language to describe your requirements for the system under the test.
Yes.
It's kind of the formal language.
Yes.
Can you tell us this language?
It is Erlang. It is Erlang. Just I have in my thesis. I have. Okay, but there was one thing. I was missing here because I, I have to tell you, I actually found more than 100 faults in that location system I was talking about at the beginning. Sorry, you were talking about a formal language, and I'm using Erlang. And in my thesis here, you can write all about this, the semantics and the syntax of the language that I use. So,
Thank you.
okay, thank you.